I think we shall begin now. Okay. Assalamualaikum warahmatullahi wabarakatuh. May peace be upon you. Salam sejahtera, ni hao, and a very good afternoon I bid to everyone. My warmest welcome to our distinguished speaker today, Professor Congo Tak Shing CHING from National Chung Hsing University, Taiwan. I would like to thank you, Professor, for spending your precious time with us despite your busy schedule. I have never met Professor Congo in person, but we are going to have more MOA and MOU with National Chung Hsing University soon. To all our viewers out there, thank you for joining us in this auspicious event, UTM Engineering Distinguished Lecture Series, brought to you by Faculty of Engineering UTM. And for your information, today's series is our 78th series. I am Masnida Abdul Wahab, streaming live from School of Biomedical Engineering and Health Sciences. It is my utmost pleasure to be given this opportunity to moderate today's session. And for those who have joined us, let me brief a bit about this series. Distinguished Lecture Series is initiated by Faculty of Engineering since June 2020. Since then, we have invited many distinguished professors worldwide to share their expertise and their experience virtually due to COVID-19 pandemic. We are proud to be able to bring in professors from 26 countries so far under this platform. So please like and share this prestigious live event within your network, and we hope that we could reach as many people as possible since Prof. Congo will share with us on something interesting shortly. With us today, streaming live from UTM, we also have our respected Dean, Yang Berbahagia, Professor Dato' IR, Dr. Muhammad Rafiq Abdul Qadir, to welcome our speaker. Without further ado, I would like to invite Yang Berbahagia Dato' to introduce Professor Congo to all our audience today. Over to you, Dato'. Thank you.
Thank you, Dr. Asnida. Assalamualaikum warahmatullahi wabarakatuh. Hello, welcome everyone. Welcome to our 78th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering University Technology Malaysia. Today, it is my utmost pleasure to welcome Professor Congo Tak Shing CHING from National Chung Hsing University, Taiwan. A bit about our distinguished speaker today. Dr. Congo Tak Shing CHING was born and brought up in Hong Kong. He received his bachelor degree in Prosthetics and Orthotics with first-class honors from the Hong Kong Polytechnic University in 1999. After completing his bachelor, he joined a private rehab center in Hong Kong as a part-time Associate Prosthetist-Orthotist. At the same time, Dr. Ching studied a master's degree and received his MPhil degree in Biomedical Engineering from PolyU in 2002. He then moved to the UK to pursue a PhD from the Bioengineering Department, University of Strathclyde, Glasgow. He completed his PhD in 2005, specializing in biomedical electronics and instrumentation. In the same year, he has been awarded the first Medical Devices Faraday Colorado Fellowship by the Department of Trade and Industry, UK, to work as a Post-Doctoral Research Fellow at the University of Colorado at Denver and Health Sciences Center, US, in learning the American legal, regulatory, and understanding the reimbursement environment for biotech and medical device. In 2006, Dr. Ching got a funding from the Royal Society of Edinburgh in UK to work at the University of Strathclyde in Glasgow in the Department of Bioengineering as a Post-Doc Research Fellow. In 2007, Dr. Ching got an academic position in Taiwan, and he is now a professor and the head of Graduate Institute of Biomedical Engineering, National Chung Hsing University, Taiwan. His research interests are in biomedical instrumentation design, biomedical electronics, biosensors, tissue bioimpedance, non-invasive and transdermal metabolites, biomarkers extraction, and drugs delivery and assistive device. So that is a brief biography of our distinguished speaker today. Here now is Professor Congo Tak Shing CHING from National Chung Hsing University, Taiwan, on the application of electrical impedance measurement on biomedical field. Professor Congo Tak Shing CHING, over to you.
Okay, thank you so much for the introduction, Professor Rafiq. So first of all, welcome for all of you to join my talk. And first of all, I need to thank you so much for the UTM to give me the opportunity to share my upward experience on the application of the bioimpedance on biomedical field. So my name is Tak Shing CHING, and I come from the wait for me. Let me share my graph. Okay. So I come from the National Chung Hsing University in Taiwan at the Graduate Institute of Biomedical Engineering. Today, I will try to give a talk on the application of the electrical impedance measurement on biomedical field. I think most of you may not be in Taiwan and even don't know where. Yes?
Sorry to interrupt. I think you haven't shared your PowerPoint presentation.
Okay, no problem. Let me share. Yes. Okay.
Right, and then your PowerPoint. Excellent, and then the slideshow. Excellent.
Okay,
You can proceed.
Okay, sorry. Thanks for the reminding. So, so maybe you don't know where is the locations of the National Chung Hsing University. Actually, NCHU is located at the center of the Taiwan, which is around 1 hour distance from the Taipei, and also the same hours for the Kaohsiung, where they have the international airport. So that, for example, if you want to go to Malaysia, you can just simply take an international flight there. In our campus, we have a net. We have a NIC at the center of our campus, and you can see here is the main gate of our university. So behind our campus, we have a river which can allow us to have the canoeing there, and also we can have a very attractive landscape at our university. So we are based at the buildings of the applied technology. So next time if you go visit an NCHU, please don't forget to visit us. Here is the outline of my today's talk. First of all, I will talk about what is bioimpedance, because most of you may not know what is impedance and even don't know how we can apply the impedance onto the biomedical method. That is the reason why I need to explain some of the ideas on bioimpedance first. Then I will talk about how, on my research on how I apply the impedance on measuring the oral cancer, skin cancer, pressure sore, as well as the low back pain assessment. Because in order to measure all these kinds of pathological conditions, we need to use the sophisticated device, but not all the people can have this kind of device. That is the reason why at the end, we developed our own 2D bioimpedance imaging systems, which can allow us to convert all these kind of bioimpedance data into a 2D image. So right now, do you know what is bioimpedance? Actually, it's very easy, because as we all know that all the matter in the world, if its temperature is over the absolute 0 Kelvin degree Celsius, then it will have its impedance. In order, the same as for our tissue, body tissue. So in order to measure the impedance of our tissue, we can just using 4 electrode configuration like this diagram. So for the 2 ultimate jet the constant AC current into the tissue, and by the use of the 2 innermost electrodes in order to measure the potential difference across the tissue. And by the use of the Ohm's law, V is equal to IZ, because the current we give it and the voltage we measure it. Of course, we can simply calculate the impedance of the tissue. So right now, I will talk about what's the application of the bioimpedance. Of course, the most well-known one is the body fat measurement. In the past, without the use of the bioimpedance to measure the body fat, we're using this kind of clip, and sometimes it is a little. That is the reason why nowadays most of the people using this bioimpedance body fat meter, and normally it also employs the excuse me. 4 electrode configuration. As you can see that 2 hands will grip onto a right, and the 2 feet will step onto the electrode, and there's a current to pass through the whole body. As you can see from this small diagram, our body segments can actually be separated into several equivalent circuits, and when we try to inject the current into our body, then we can simply measure the impedance of our body. So by the use of the empirical formula, of course, we don't know it because it is the treasuries of the company. So we can use the empirical formulas to calculate it best, the body fat content. Normally, the currents to inject into our body is at a level of about 0.1 milliampere at a frequency of 50 kilohertz. So other than the well-known body fat meter, by the use of the impedance, Actually, there is another well-known device which also employs the impedance to measure for the biomedical field. For example, the impedance can also be used to measure the amount of the cell in a suspension, and the most well-known machine is the Congo Tak counter. As you can see from this diagram, let's say if we have a tube of the red blood cell and we want to know how much, what's the amount of the red blood cell inside the test tube, then we just simply put into this container, and then we try to push or give a pressure and let the red blood cell to pass through the membrane, which this membrane will separate these two chambers apart. So before the red blood cell pass through the membranes, because they have a wider there's a wider space, so the current is easy to pass through. It means that it will have a low resistance. But when the red blood cell just passed through the membrane, it will have a narrow pathway. So it means that the impedance will increase. So by the use of these techniques, we can count how many number of red blood cells is inside a test tube. Of course, we can also use the bioimpedance to measure whether our blood vessels is occluded. So next time, maybe sometimes if you go to the hospitals to do some body check, maybe you have already seen this kind of photo. This is the photo for the measurements of the venous occlusion physiomography. So for simply speaking, we were using the 4 electrode system, two outermost electrode, one will put it onto the thigh and one will put it onto the feet. And the 2 innermost electrodes will put it onto the tibia regions. And we'll apply a cuff here. So when the cuff increases pressure, it will press the blood vessel and there is no blood go into the tibia regions, so its impedance will decrease. But when we release the pressure of the cuff, the blood can go back into the thigh and its impedance will be increased. By the measurement of the slope of these 2 slopes, we can simply note whether our blood vessel is occluded or not. Just for example, by the use of this deflated outflow rate, we can note whether the patient is suffering from the deep venous fibrosis. Other than that, people can also use the impedance to measure the stroke volume of the heart, which is so-called the impedance cardiography. And normally we will put 2 electrodes on the net and 2 electrodes onto the trunk, and the 2 outermost electrodes will inject the current and the 2 innermost electrodes will measure the potential difference. And by the use of the empirical formulas, we can calculate the stroke volume. And last but not the least, we can also use the bioimpedance to measure the breast cancer. And one of the machines which is FDA approved and its name is Scans TS2000, which is employs the use of the bioimpedance to document whether a woman is suffering from the breast cancer. And this machine actually is from the Siemens. So right now, after you know all the applications of the bioimpedance, then I need to let you know its working principle. As we all know, that the basic unit of our human body is the cell, and the cell consists of the cell membrane. So here in front of you is the cell membrane. It consists of the protein channel and a lipid layer. For the protein channel, if it is open, then the fluid can go in and go out. But if the protein channel is closed, the fluids cannot go in and go out. So it means that we can simply using a resistance to represent the protein channel. When it is open, it has low resistance, but when it is closed, it will have high resistance. So how about for the lipid layer? For the lipid layer, because it will block all the DC current, but not the AC current. So for the electronic components, we can simply using the capacitors to represent the lipid layer, because all these layers are connected in series. So it means that we can simply make a parallel combinations of the resistor in connection with the capacitors to represent a cell membrane. So right now, let us have a look on a whole cell, because for the whole cell, it has the cell membrane like this. So it will have 2 parallel combinations of the resistor together with the capacitor. So how about for the intracellular and extracellular fluids? Because all these fluids contains a lot of ions. That's why we can just simply using a resistors to represent them. So to simplify this circuit, we will have this simplified circuit. But as we all know that most of the times the protein channel may not be open. If it is closed, it means that it will have a very, very high resistance for its cell membrane. So to further simplify this top circuit, we will get this simplified circuits to represent our single cell. So right now, I will talk about how I will apply this kind of model on documenting just oral cancer, skin cancer, etc., and etc. So right now, I will talk about how I use the bioimpedance techniques to measure the oral cancer. As we all know that oral cancer is very common, and it holds the sixth most frequency occur. It is the sixth most frequently occurs oral cancer all over the world. And for the oral cancers, the tongue cancer is very common as well. So just for example, in Taiwan, in the past decade, the prevalence of the oral cancer increased up to 160%. But not just the prevalence, but also, not just for the prevalence, but also for the mortality. It also increased 110% in Taiwan. So because of this problem, that is the reason why I'm focusing on documenting whether we can using this kind of non-invasive bioimpedance techniques to document whether a patient is suffering from oral cancer. So in order to know whether a patient is suffering from oral cancer, for the routine clinical practice, they were just simply using the eye, of course, to see whether we have the right spot onto on the tongue. If you have a single white spot, it doesn't mean that it is oral cancer. But when you see this photo, you will see that definitely it is oral. Definitely, you may suspect the patient is suffering from cancer. But when you find this kind of situation, it is already at the latest stage. That is the reason why most of the patients, when they discover they're suffering from oral cancer, it is already at the latest stage, because we normally using the net eye to inspect whether we are suffering from oral cancer. So how we conduct the experiments to see whether we can using the impedance to document the oral cancer. So by the use of the precision impedance analyzer, of course, we also need to develop our own probes. And for our probes, we using 4 electrode configurations, and these electrodes are made by gold because they are inert. As I described before, we have the mathematical model. We have the equivalent circuits to represent our cell, one cell, and for this equivalent circuit, it will have its mathematical equation here. So based on this equivalent circuit, as we can find that for the current, if it is a DC current, so all the currents can only flow up but not flow down because of the capacity at the lower portion. So where is the upper portion? The upper portion represents for the resistance of the extracellular fluids. So it means that if we pass a DC current or we pass a low frequency current, most of the currents will flow through the extracellular pathway rather than the intracellular pathway. Okay, so in these experiments, we try to use the frequency as low as 20 Hertz. So how about at very high frequency? At very high frequencies, the capacitor can be looked like as an inductor. It means that the high frequency currents can not just flow through the upper portion, but also the lower portion. The lower portion represents for the intracellular area. So it means that we can change the frequency in order to let us to find out the intracellular resistance. In these experiments, the highest frequency we use is the 5 megahertz. Once we measure the impedance at the low impedance and at very high impedance, then we can simply calculate the extracellular resistance as well as the intracellular resistance of the cell. Because of the subject-to-subject variation, that is the reason why we need to normalize all this kind of tissue. And for simply speaking, we can just take a ratio on this extracellular to intracellular resistance. Then we can eliminate all this kind of subject-to-subject variation. So the finding tell us that the extracellular resistance of the cancerous tongue tissue is significantly smaller as compared to its surrounding normal tongue tissue. This is the finding what we get. Why? It's very simple. Let us have a look on this diagram. So the red line represents for the high frequency current, and the green line represents for the low frequency tissue current. As we all know that the low frequency currents will pass through the extracellular space. So because the cancellous tissue normally is loosely packed, so it means that the intercellular space will have a wider space for this kind of low frequency currents to flow through it. That means it has a lower resistance. That is the reasons why the extracellular resistance of the cancellous tissue is significantly slower as compared to the surrounding tongue tissue. So how about for the intracellular resistance of the tissue? So there's no significant difference. But as I described before, because of the subject-to-subject variation, it is no good to just using the absolute resistance value. That is the reasons why we need to take a ratios for this in order to eliminate the subject-to-subject variation. So for this ratio, we can find that the cancellous tongue tissue still have a lower ratio as compared to the surrounding tissue. So in the future, when we try to measure a tissue and the ratio is below 200, you may suspect that tissue may have pathological problems. If the ratio is at about 300 up to 400, it means that it may be normal tissue. So other than using this kind of techniques to measure the tongue tissue, we also using a fixed value, fixed impedance, fixed frequencies to measure the impedance of our tongue tissue. So the frequency we use is from 20 Hz up to 5 megahertz with 50 kHz, 1.3, 2.5 megahertz, and 3.7 megahertz. So let us have a look on this diagram. We can also find that at low frequency, the cancellous tongue tissue has significantly lower impedance. It is absolute impedance value as compared to the patient's healthy tongue tissue. And the patient healthy tongue tissue is almost the same as the normal subject's normal tongue tissue. So not just have this kind of phenomenon measure to be observed at 20 Hz, but also at 50 kHz. So you can see that 20 and up to 50 kHz is low frequency. That is the reason why we described previously. Low frequency currents pass through the extracellular pathway, and that is the reason why for this cancellous tongue tissue, they are loosely packed and they have a wider base for the currents to flow through, and it has lower resistance. Okay. So other than that, we also find that the impedance change is mainly due to the wheel part of the impedance rather than the imaginary part, as shown in this diagram. So after I talked about how we use the impedance to measure the oral cancer, right now I will talk about how we can use the impedance to measure the skin cancer. As we all know that the skin cancer holds the 6th position of the cancer death all over the world, but actually it's not that serious in Taiwan. It holds the 21st positions. In order to know whether a patient suffering from skin cancer or not, normally for the routine practice, the medical doctor needs to use the skin biopsy test, and it is the gold standard test. But this test is invasive. So because of invasive, so the patient may feel pain, and after they have the biopsy, there may be some scar on the tissue as well. And the most important thing is it is not real time to give out the result, because they need to take the sample to the laboratory to evaluate. And so the patient needs to wait for a long time to get the result. And this will give a lot of pressures for the patient. In order to solve these kind of problems, and in order to have the real-time and non-invasive techniques for the skin cancer screening, we try to see whether the bioimpedance technique is can help the medical physicians to document it. So right now, I will talk about how we establish a model, animal model, in order to induce the animal models to suffering from the skin cancer. And the animal model we use is the SD rat with the age of about 9 weeks old. And we try to use the methods similar to the filler. methods in order to use some chemicals to induce the skin cancer onto the rat skin. And for the impedance measurement, we will try to measure the impedance within the frequency range of 3 kHz up to 1 megahertz. So as you can see from this diagram, after we induce the chemical onto the rat skin, the rat skin have some papillomas. It means that the skin is beginning to have the cancer tissue there. And during the whole treatment, during the whole experiment, there is no notable reduction in its activities and also illness and loss on the rat. So here is the results to show you that the skin impedance of the rat, and we find that there is 2 characteristic frequency, one which is at 4 kHz and one is at around 50 kHz, and these 2 frequencies can tell us that the cancerous skin tissue has lower impedance as compared to the control side. So why the cancerous skin tissue have low impedance as compared to the normal skin is very easy, as it is almost the same as what we have described for the oral cancer, because the skin have cancer tissue, and the cancer tissue is loosely packed, and sometimes it even have metastasis, so the intercellular space is wider. So that's why the currents to flow through the extracellular space become wider. And the currents to flow through the extracellular space is the low frequency current. It means that at low frequency, it will have low resistance for the cancerous skin tissue. Okay. So again, it is not that good to use the absolute impedance values for the comparison. As you can see that if we use the absolute impedance values to measure, and sometimes the impedance is high and sometimes it's low. So that is the reason why we need to use the self-normalization techniques to find a ratios to represent for the cancerous skin tissue and for the healthy skin tissue. For this ratio, you can see that the red bar represents for the control side. It means the healthy skin. You can find that throughout the whole experiment, the ratio is almost constant, but not for the cancer side. The ratio decrease with date. It means that as we try to induce the skins to suffering from cancer and the cancer cell become more and more, its ratio will drop from 9 down to around 8. So next time, if we want to see whether a skin is suffering from cancer or not, we can simply measuring this ratio, and if this ratio is above 10, it means that it may be a normal, healthy skin tissue. But if this ratio is below 8, it means that it may be a cancer tissue. So in order to see whether this kind of data is reliable, we use the ICC test to test the intraradar viability. As you can see from this table, the ICC value is over 0.9. It means that all the measurements for the impedance values at low frequency and even on the ratio is reliable. So right now, I will talk about how I used the impedance to document the pressure shock. So what is pressure shock? Who will suffer from pressure shock? As we all know that for the people who are immobilized, for example, because of the spinal cord injuries, they need to lie down on the bed all the time because of the pressure point. There's no blood circulation at that pressure point, and the tissue may die, may be necrosis. So you will see that this is very serious pressure shock. So in order to see whether the impedance can document the pressure shock, we try to recruit some patient with the pressure shock. So let's say this circle is the pressure shock. Around the we will put 4 sets of the electrode, 2 sets of the electrode which is close to the pressure shock, and another 2 sets of the electrodes will be far away from the pressure shock, so that to see whether is there any difference between the impedance measured at this kind of regions. So again, we also using this equivalent circuit and the mathematical models to analyze the data. And we measure the impedance at low frequency and the impedance at high frequency as well. So as you can see that these two lines represents for the two set of the electrode close to the pressure sore, and these two set of the line represents for the two set of the electrode far away from the pressure sore. You can find that the impedance of the tissue close to the pressure sore is significantly smaller as compared for the impedance of the tissue far away from the pressure sore at a particular frequency. And what is this particular frequency, which is at low frequency again, is at about of 30 Hertz up to 125 Hertz. So why the pressure sore tissue have a lower impedance as compared to the healthy tissue is very simple, because as we know that during necrosis, all the cells die and the intercellular space increase. So the low level current, do you still remember low frequency? So the low frequency current can flow easily through the intercellular space, and that is the reason why for the impedance of the tissue close to the pressure sore have low impedance. Okay. So again, we also want to see the extracellular resistance. You can see that, let's say if here is the pressure sore and this is the impedance close to the pressure sore and this is the impedance far away from the pressure sore. So you can find that the extracellular resistance of the tissue close to the pressure sore is significantly lower as compared to the tissue far away from the pressure sore. So again, this is exactly the same what I have explained for you, why the impedance of the tissue have low impedance. So I don't want to explain it here furthermore. So how about for the intracellular resistance? There's not so many changes. In order to normalize all this kind of tissue, you can also find that this ratio for the tissue close to the pressure sore is significantly low as compared to for the tissue far away from the pressure sore. Okay, so right now I will talk about how we will using the bioimpedance to measure the low back pain. So as we all know, that the low back pain most of the time is because of the muscle inflammation. So we also using these models to analyze whether the impedance can be used to document the low back pain. That is, therefore, we try to using the low frequency. The frequency is at 20 Hertz to measure its impedance, and also using 5 megahertz of the frequencies to measure its impedance at high frequency. And we can find out all the extracellular resistance, intracellular resistance, as well as the ratio. So because most of the times the muscle pains may be happened at the paraspinal muscle, that's why we stick the electrode onto the paraspinal muscle. And all this patient has been confirmed that their low back pain is because of the muscle inflammation. So after we measure, we find that the low back pain patient, the low back pain patient have a lower resistance for the paraspinal muscle as compared to the healthy subject. So why? Because as we all know that during inflammation, the cell may have repairing protein. And other than that, during inflammation, the local areas you will find that the local area will feel warm. This is because a lot of blood will flow through to these regions in order to help the cells to become better. Okay, so that's why if we have a lot of blood to flow through these regions, it means that we have a lot of ions to flow through the intercellular space. It means that the resistance will drop as well. That is the reason why you will find that the low back pain patient will have a lower impedance for their paraspinal muscle as compared to healthy people. Okay, but how about for the intracellular resistance? You will find that the intracellular resistance for the low back pain patient is a little bit higher as compared to the normal people. Why? This is because that they have the repairing protein. So the repairing protein increases its impedance for their intracellular resistance. Okay. So we are also using the self-normalization techniques to see whether there's significant difference, and we find that there's significant difference as compared for the ratios of the low back pain patient with the normal subjects. So right now I will talk about how we developed our impedance analyzing system in order to document whether a patient is suffering from pathological problems. Here is the architecture of our imaging system. So we have a probe, we have made a 8x8 array configuration probe, and by the use of the multiplexer in order to switch this array, and we also developed our impedance measurement circuit in order to measure the impedance of the superficial tissue, and all the multiplexer and the bioimpedance measurement circuits will be controlled by this control unit. Okay, so after converting all this kind of data, analyzing, calculating the pixel, then we transmit to the computer through the ZIP-B. So you can see that here is the whole system. Here is the hardware, and the software of course stored inside the computer, and you can see that this is the probe. So for the probe, we have 8x8 array, and all this probe is made from gold. So because gold is inert, that's why we will have a better impedance measurement result. And for each cell, we will have 4 electrode. It means that we use the 4 electrode configurations to measure the impedance. 2 electrode is injecting the current, and 2 electrode is measuring the potential difference. So here is the working interface for the software. We use the Visual Basics to write the software, and as you can see that here is converting the impedance data into the 2D image, and as you can see that you can you can see from this histogram, all these lines within these 2 lines represent they are normal. Outside these 2 lines, they are abnormal. You can find that this data is abnormal because out of these 2 lines, and this data is abnormal. And here is the coordinate of all this kind of cell. So this software not just tells you whether this value is normal or not, but also tells you the location as well. For the accuracy of the systems, we have compared with commercial precision impedance analyzer. As you can see, we try to measure the impedance of a substance from low frequency to high frequency. We have a very, very small percentage error as compared with the precision analyzer. It means that our system is very accurate. Also, we also using the BA pros to test the reliability of our system. As you can see that all the measured point is within the 2 standard deviations line. It means that our measurement, all the data measured by our system as compared with the commercial precision impedance is variable. So we also using the in vitro test to see whether the system have the abilities to locate it as well as to document it. So we have the agar gel, and with the agar gel with high resistance and low resistance at the center. So you can see that it can locate the location as well as to show you this is the pathological tissue. So we also using the prosthetile skin and the prosthetile tongue, and by the use of our systems to measure the impedance of the prosthetile skin and prosthetile tongue. So if we done nothing for the skin and the tongue, the impedance is normal. As you can see, the color is within the 2 lines. But after that, we try to make a scar onto the prostate skin as well as the prostate tongue. You can see that it has, because of the scar have a high resistance. That is the reason why it located. So here is all the reference from what I have for all the research I have presented to you previously. And of course, I need to thank you for some of the organizations, for example, the Ministry of Science and Technology, because they provide me the fundings for all this kind of research, as well as I also need to thank you all these kind of scholar in Taiwan, and also I need to thank you for my students, because without them I don't have all this kind of data. And last but not the last, I just want to tell all of you, next year we will hold a conference in Taiwan, and the conference will mainly focusing on the engineering and technologies for healthcare. So if you have time, please try to join our conference. So that's all for my presentation, and it's the time for the question and answers.
Thank you, Professor Congo, for the very insightful sharing. We will now take any question from our audience. Do we have any question? Okay, so probably while waiting for the questions to appear on the screen, I would like to ask you one question regarding your research. Professor Congo, you were mentioned about the skin cancer, yeah? To measure the skin cancer. May I know whether these electrical impedance can go deeper to probably detect a breast cancer, since they have different tissues and density? Is it possible?
It depends on the electrode distance. As at the beginning of my presentations, you can find that Siemens already have a device, TS2000, which is by the use of the impedance to document whether a patient is suffering from the breast cancer. So this kind of technique actually can be used for the breast cancer. But of course, it's not that deep, because the distance for my two electrode is very close together. As I still remember, is at the distance of about 10 millimeters. So it is just a superficial tissue, very, very superficial tissue.
Okay, thank you, Prof. Okay, we have one question from Adeline Tan. Can future electrode help the immobilized patient to move?
Can future electrode help immobilize patient to move? Actually, I'm not really understand his question, but I will try to answer. Is that means can electrode help can electrode help immobilize patients to move, right? Of course, yes. But the use of the functional electrical stimulation, yeah. But this is not the application of the bioimpedance, because today's my topic is the use of the bioimpedance for the documentation of the tissue. For this one, actually, it is related to the physiotherapist, by the use of the electrical stimulations to stimulate, for example, the muscle tissue in order to let it contract, so that's to let them to move. Yeah, it is possible.
Okay, thank you, Prof. Can we take more question? One or two more questions? Okay. While waiting for others, I have more question for you, Prof. It's very interesting topic. I did some study on this in my PhD time, but yet to use the impedance for my study. Okay, when you converted those signal into your 2D image, yeah, it is basically what you see on the surface. Again, yeah, on the deeper cancer, for example, breast cancer or any other cancer that exists or present at the lower part of your skin, is it possible for us to get the slicing of that, images by playing around with the current and so on?
Oh, I'm so sorry to tell you that this system have its limitation. The 2D imaging systems can only allow us to measure the superficial tissue. As you can see, the probe, the 256 electrode is very well close to each other, with the distance of above 2 millimeters. So it means that because of the distance between these two electrode, the electric fields can only just go maybe 1 millimeter deep, or maybe even lesser. So that is the reason why for this 2D imaging system, it is impossible to go deeper tissue to document whether the pathological change of the deeper tissue.
I see. Okay. All right. We have a question from Tan Ai Yi. Different person has a different amount of subdermal fat and fat affect impedance. So how do you deal with these varying impedance when dealing with different type of skin?
That is a very good question. So when we try to document whether the skin is suffering from cancer, we are not just trying to measure the absolute impedance value. So if you still remember the graph I showed you, I find two characteristic frequency which can document the skin cancer. So we try, because for example, if here is the skin cancer, we try to measure the impedance of the impedance of the tissue at as I still remember, is 4 kHz, and also measure the impedance at 40 kHz. So because we measure the impedance on the same patient, so when we try to using the self-normalization technique, we can eliminate all these kind of subject to subject variation. That's why there will be no problems on comparing the data. But if we use the absolute value, definitely it will dramatically affect. Just for example, young people as compared to the old people, even they are healthy skin, they will have totally different impedance. But by use of the self-normalization techniques, it can eliminate all this kind of problem.
Okay. Thank you, Prof. Congo. Okay, do we have any more questions from our audience? Okay, we have a few more minutes left. So please take this opportunity to ask Prof. Congo questions. Okay. Okay, now I have a question again on your research on the equipment that you use to measure the electrical impedance, because you're using one probe, right? The one single probe to get the screen, the signal from the skin surface. Is it possible for us, for example, to use two probes? I mean, one receive, one transmit, in order for us to get better data?
Actually, I also for the skin impedance measurement, I'm using four electrical configuration. Yep. So 2 to injecting the current and 2 measuring the percentage difference in order to calculate the impedance. It's because of the 4 electrical configurations, the electrical impedance can be ignored. That is the reason why most of the times I will use 4 electrical configuration. 4 electrical configuration. Only although we have one pole, but have 4 electrodes there. Yeah.
Okay. Also, is there any possible for us to use different configuration? For example, circular type of arrangement of the electric than 4 by 8 by 8 by 8 by 8. Sorry.
Yeah, of course, we can use different configuration, of course, as long as we obey, for example, 2 electrical configurations or 4 electrical configuration. So either in triangular shape or in rectangular shapes, but most of the times we're using the rectangular shape or a circular shape. Yep.
Okay. So shall we take more questions? Okay, we have no more questions so far. Probably you would like to. I would like to know about the safety of patient. Yeah, when we talk about injecting current, to how what is the maximum range that you can go to get as deeper as possible a signal from patient.
Okay, so for my 2D imaging systems, the maximum current we can inject into our body is at about 1 milliampere. Yeah, which is within the safety limit.
Okay, so there's no way for us to increase the accuracy. I mean, looking at the image that you shared just now, when the skin when the star is circle, but the conversions of the signal it seems pixelated. What can we do in future to make sure it's really giving us accurate result?
So we say like that for the safety reason. Actually, in order to measure the impedance of a method, there is 2 approaches. One is the constant current approach, and one is the constant voltage approach. For me, the 2D imaging system is using the constant current approach. It means that no matter the impedance change for your tissue, the current flow through the tissue is still keep constant. We just try to measure the potential difference across the tissue. That's why it can increase the safety issue for the patient. Yeah.
Okay. I think there's no more question from the audience. Okay, so I think that's it for today. Again, I would like to thank you so much, Professor Congo, for your fantastic and insightful sharing with us on the electrical impedance measurement for biomedical application. Thank you to all our viewers, wherever you are, for joining us today and for participating in this Q&A session just now. And if you want to hear more from Professor Congo, he will be with us again next year, virtually as a keynote speaker for our iMedis conference that will be held in June 2021. Yeah, you may refer to the link provided in the chat box to check out both iMeditech and ICBME conference, which the main focus is again on the research related to biomedical engineering and its application. That's all from me, I think, and I will pass back this session to our Dean, Professor Rafiq Abdul Qadir. Over to you, Professor. Thank you.
Thank you, Dr. Asnida, for moderating this session, and to our friend, Professor Congo, all the way from Taiwan. Thank you so very much for accepting our invitation, and thank you for a great sharing session. We have, by the way, Congo, we have more than 200 unique viewers watching your webinars.
Oh.
So there you go. So it's a very interesting talk, and it's a pity that we cannot meet again due to this COVID-19 pandemic. By the way, to all of you watching this series, we have a very good collaboration. UTM and the Biomedical Engineering School has a very close collaboration with the Department of Biomedical Engineering in NCHU. So we have visited NCHU for several times now. So we hope that the collaboration can continue well into the future. So thank you again, Congo. And to all of you, all the viewers worldwide, thank you for watching UTM Engineering Distinguished Lecture Series. Do stay tuned because we have many more interesting lectures for you. Until next time, bye-bye for now.
Okay,
Bye-bye.
Thank you so much. Bye-bye.
Thank you, Prof.